So in this video I want to explain the theorem for counting positive solutions. Okay, so problem is like this. How many solutions for equation like this? Yep. So we've got k variables, x1 up to xk, and the sum of them is supposed to be n. And each of these variables is supposed to be strictly positive, and it's also supposed to be an integer, right? See, if we allowed real numbers, there'd be infinitely many solutions, but we're just allowing positive integers. So let's just try an example. Suppose we want 4 variables adding up to 6. Okay. So what could it be? So you could have a you could have 1, 1, 1, 3. So you've got 3 ones on a 3 like that, and then symmetrically you could have 1, 1, 3, 1, or 1, 3, 1, 1, or 3, 1, 1, 1. Okay, that's one way we can do it. That's 4 possible solutions. But that's not all of them. So another thing we could do, instead of having 3 ones on a 3, we could have some 2s. Okay, we could have 1, 1, 2, 2. Or 1, 2, 1, 2, or 1, 2, 2, 1, or 2, 1, 1, 2. Yeah, where are we at in there? Or we could have 2, 1, 2, 1, or 2, 2, 1, 1. Okay, so it's 4 of this type and 6 of this type, and altogether 10 solutions. Okay. But we don't want to be having to kind of spell everything out like that in the general case. So we want a theorem which will tell us the total number. And so the theorem is like this. Total number of solutions is the binomial coefficient. N minus 1, choose k minus 1. Okay, and so how do we prove this? Okay, so we given a solution, say like that. What do we do? We we take the interval from 1 up to n, and we divide it into intervals of length x1 and then up to xk, right? We've got a first interval of length x1, the second interval of length x2, all the way up to the last interval is going to be of length xk. Okay, and then because the sum of the xi's is equal to n, then those intervals, they cover the whole thing. And then let's put A as the set of endpoints, or right-hand ends. Okay, we take each of these intervals. We've got k intervals, and we take and each one we look at the right-hand end of it. And so those could be somewhere in the set 1 up to n. Now the last interval is not very interesting. The last interval, of course, has to end at the right-hand end of the whole block at n. So that's not really telling us anything, the fact that the last interval ends at n. But the endpoints, so we ignore that last interval and we just consider all these guys. So these, if you think about it, they're in the set 1 up to n minus 1. Okay, and we can't have n can't appear. N is the endpoint of the last interval, and the previous intervals they all have endpoints that are before that. Okay, okay. So now we've got this A. Right, we're going to need some more space. So this gives us a subset A of size k minus 1, right? It's k minus 1 because they were k intervals and we ignore the last one. So we've got k minus 1 intervals and we take the endpoints of those, k minus 1. Okay, so this so for every solution we get such a subset. So this construction is giving us a bijection between these solutions. The number of solutions is equal to the number of subsets of this relevant kind. And the number of those subsets, of course, is n minus 1 choose k minus 1. So let's just see how it works out in the case that we were interested in. Okay, we're saying that solutions for x1 up to x4 equals 6. Because they biject with subsets of size 1 less than the number of variables, which is 3, in 1 up to 5. Okay, so as an example of that, you could have like 1 plus 3 plus 1 plus 1. Okay, and so what we're supposed to do to translate that in, so this we've got this solution here. This is one solution to our equation, and so we're supposed to think how that corresponds to a subset. So what we do is we draw one, two, three, four, five, six, okay. And we divide that into intervals. We've got one interval of length 1, corresponding to that 1 here, one interval of length 3, and then 2 more intervals of length 1. And then we look at the endpoints of those intervals. Okay, so so we ignore the last interval, but apart from the last interval, so we've got this endpoint, and this endpoint. So this corresponds to the set 1, 4, 5. Or another one of our solutions could be, say, 1 plus 2 plus 1 plus 2 is 6. So what subset does that correspond to? Right, so again, we draw 1, 2, 3, 4, 5, 6. And we divide that into intervals. First interval of length 1, second interval of length 2, third interval of length 1, and fourth interval of length 2. And yeah, and then we look at the right-hand ends of all these intervals except for the last one. And so we've got ignoring the last interval, we've got 3 intervals and 3 endpoints. So we get this set here, 1, 3, 4 of size 3. So we're seeing that there's a bijection between the solutions for this equation that we're looking at and the subsets of size 3 and 1 up to 6, sorry, 1 up to 5, yeah, because we never get 6 out of this. So the total possible number is 5 choose 3, and 5 choose 3 is 10. And at the beginning of this little video, we just actually wrote down all those solutions and we found that there are 10 of them, so it all matches up.